The New Quantum Era,
a podcast
by Sebastian Hassinger
and Kevin Roney.
Welcome back to the podcast. This is Sebastian again. I've got a couple of episodes for you. Kevin will be returning. We actually have recorded an episode this week that I'll be cutting together and posting early next week. But in the meantime, back in April, I went to a workshop at the Simons Institute for the Theory of Computing at the University of California, Berkeley. They had a week-long workshop on near-term quantum computers, fault tolerance and benchmarking, and quantum advantage and quantum algorithms, which was fantastic. There were a ton of really good talks, great presentations, great speakers, and the Simons Institute was kind enough to provide for me a space to record, and I grabbed a couple of the guests, the invited guests who were giving talks and recorded these interviews. Today's is going to be with Jens Eisert, and he is a professor at Freie University Berlin. And you'll hear, again, a little flustered with trying to set up the space. I didn't do a proper introduction, and I apologize to Jens, but we had a really great conversation about his work. He's been really a pioneer from very, very early on. He's been in the field for something like 20 years. He's been doing a ton of work with his group at the Freie Universität. And we talk, it's a pretty wide-ranging conversation around the work that he's been doing around benchmarking, verification, sort of the limits of the variational and NISQ algorithms and other topics. So I think you'll enjoy. Thanks for joining us, Jens. Can you start just by sort of a brief introduction?
Well, the pleasure's on my side. Thanks for inviting me. My path, do you mean my biographical path?
Sure, yeah.
So in a way, I'm a veteran of the field, you can say, in that I did already my PhD in quantum information science on the role of entanglement in quantum computing and quantum communication. And when I started, the field was still quite young, although not that young. Some of the big results had been achieved, but I was doing other work on open quantum systems before. And then when I found this field, I was super excited and was hiding in the library for weeks, reading all the papers I could find for at the time. And then I was hyped and wanted to work on this. And then I arranged things, and since then I've been in the field. That was more than 20 years ago already, and since then I've been thinking about the subject, and now also leading a team that's in a way rigorously minded, working with the ideas of mathematical physics, but at the same time being pragmatically motivated on the protocol, on the phenomenon, on things that exist, and sometimes even work with experimentalists, and that's kind of our place in the community.
Yeah, so is it fair to say that you are more, you're trying to establish theoretical sort of limits or guidelines to what we can do with the hardware that exists today? Is that a major area of focus?
My research interests are pretty broad, but my talk was about that today.
Yeah.
That's right. So I'm interested in what we can do with quantum computers in the long run, but also in the near term. What goals we could find, what things we can do that may have practical applications on the one hand, but I'm also interested in finding the limitations, finding the fine line between what's just not possible or what's possible.
Right.
And also to see the fine line between the classical world and the quantum world. And the development of the last years have been extremely exciting and productive. And I want to see how things go forward, staying away from the hype, because there's also a bit of maybe exaggerated expectations. And I'm interested in finding out what's honestly possible in the next years to see what expectations we can really see.
And is that in part motivated by the fact that, sort of the most, I would say, popular or best known approach is to hopefully get some sort of value out of NISQ machines, out of these noisy machines, are variational algorithms or techniques, VQE, QAOA, and they're heuristic, right? There's limits to what you can provably do with or accomplish with those types of approaches? Yeah,
that seems fair to say. I mean, this is a hugely exciting idea, no doubt about this. It's really difficult to make strong claims on their utility. I mean, there's no proven separation. Well, there's some, but under somewhat funny conditions. It's not so easy to make strong statements on their computational power, but it's worth finding out. And one of the research themes that we've been involved in is to kind of find out what these devices can do, and also, as I said, find limitations thereof, and understand the line of how classical simulation methods can go, and on the other side, where a regime could be identified where you can do interesting things. And even though it may be difficult to formulate the holy grail proof of really a full practical advantage of a type on a near-term machine, there's kind of proof pockets. You can prove a couple of things that are interesting that, if put together as a kind of puzzle, they give rise to a more complete picture. And then I see my job in parts on providing puzzle pieces to the big picture, hoping that if you have enough puzzle pieces together, that a more coherent picture emerges at the end of the day.
Right. And is that in part, I mean, I see that in two lights. One is to try to, as you said, sort of provide more puzzle pieces to potentially get more value out of these current devices, but it also seems like it can help inform sort of future direction of, it's almost the co-design idea of how the next generation of hardware, you're feeding ideas and observations and theory into the experimentalists' hands to try to help them and their progress on the hardware side. Is that fair to say?
That's absolutely fair to say. I mean, it's actually, it's more than that. I mean, it's true in two senses. I mean, on the one hand, we are actually providing lots of tools to kind of benchmark quantum devices. That was actually the topic of the session today, even though I decided not to speak about this, but that's a topic that's pretty present in my team, to think of randomized measurement techniques, randomized benchmarking techniques, and so on, to find out what's happening in the device. But not only that, but use that information to kind of then feed it back into the design of the device to see how you can improve things with this actionable advice acquired by the benchmarking technique, on the one hand. On the other hand, I mean, I've been mentioning some no-go results, and I don't see no-go results as killer statements. They're not meant to shoot down things. I mean, early on in my career, I formulated a no-go theory that was then much cited and so on, and people complained about this for some time, but then they realized, wait a minute, you can overcome this by thinking outside the box.
Even today, during your talk, people were saying, where's the loophole? You could tell people were sort of looking for the loopholes around your no-go statements.
Yeah. I mean, also some years ago, I had a result on quantum computing with Gaussian states. There was a kind of idea of using continuous variable quantum states to do measurement-based quantum computing. And for a large class of states of that kind, I could show that they will not work, in the sense that if you do something on one side, then the impact on the other side will necessarily decay exponentially with the distance, so that you cannot even transport information. And people got very upset about this, saying, "Oh, is this now showing that the idea doesn't work?" I said, No. I'm just saying that for arbitrary projective measurements, this is not going to happen. But these are the rules of my game. And then a couple of years later, somebody found out that if you project onto certain code words of quantum error correcting states, like GKP states, then you can actually do this, which was slightly outside my theorem.
Right.
And then it could be done. So
Right.
that was precisely the development I had hoped for, in
Right.
that I wanted to invite people to think a little bit outside the box.
Yeah.
And this also did happen.
Yeah.
And I like no-go theorems, but again, not to kind of produce roadblocks, but to motivate people to think in slightly different directions.
Yeah, I mean, that's sort of the core of the scientific method anyway, right? It's disproofs that then provoke new theories that try to get around disproofs.
Yeah, it doesn't always work out well, but
Yes.
I mean, if it works out, it's a nice development.
Yeah, exactly. And so, returning to what you're talking about today, I thought the benchmarking aspects were really interesting, and also, you were mentioning, those being able to predict the outcomes, or the distribution, of the outcomes.
Yeah.
With Clifford gates, you're able to easily predict the distribution, or to model the distribution. But as soon as you add one to Foley gate, it becomes really difficult to forecast. Is that?
No. It's even more subtle than that, in the sense that, I mean, there's a forward direction and a backward direction. I mean, let's not forget, there's a circuit, and you make measurements in a fixed basis, so you get a classical distribution from a quantum circuit plus measurements.
Okay.
And I mean, these are like sampling schemes, and like to sample from the output distribution, it's a specific reading of a classical simulation of a quantum device, and that's well understood in what precise way like Clifford circuits would be efficiently classically simulated.
Right.
There's more than one way, so in all the known ways, it's a classically simulatable thing. And you can also add T-gates. If you add not too many of them, like logarithmically many, you can still do that, and you can kind of basically keep track of the branches, and you can still do that. The converse problem is you have a distribution given, and you want to learn it in the kind of machine learning sense, or in the Puck learning sense, to put it in fanciful terms. But this is like really the kind of approach of computational learning theory, like given samples from a distribution, can you actually learn what the distribution is like in certain fine prints of this question? And then it turns out that while Clifford circuits can be efficiently learned, this is no longer true if you add one T-gate, which is like really strange and striking, because the forward direction is borderline trivial. Clearly the classical simulation is efficient because you just keep track of the branches of the quantum gate. The backward direction is not possible, you're not forced to find this counterintuitive, but it's interesting.
It is interesting.
So unsymmetric.
Is it possible that sort of lends clues to possible areas of advantage? Does that sort of suggest areas that need to be investigated for potential quantum algorithmic advantage?
Well, yes and no. I mean, literally speaking, I'm not sure. Like whether this specific result has any implication, I would be somewhat doubtful about this. Of course, that result is part of a program that is, of course, directed towards finding advantages of the type. So, also some of the, I mentioned this briefly at the end of the talk when we looked at random Fourier features. There's a lot of activity also in my team to think about new, like classical simulation methods that are not completely standard, and that kind of identify like a classically accessible regime, then like hoping to delineate the boundary of the quantum side, so that, so to say, where you can hope for quantum advantages of a kind. And this bigger program is surely directed towards finding advantages of a kind. I even mentioned this at the beginning of my talk when I mentioned like short circuit learning advantages, which is a question where you want to see whether constant depth quantum circuits have a superior power concerning certain well-defined learning tasks compared to well-defined log depth classical circuit with a meaningful locality structure. And this seems to be the case, which is, if you want a quantum advantage of a kind, it's still not the big answer because it's not very practical, and the kind of distribution, the concept class are a bit crazy and so on, but like lacking the big proof of the big statement, I think it's sensible to try to approach the question from all possible directions so that you come closer to the real thing in the middle by providing sound
and that's honestly
answers. along the way.
That makes a lot of sense, and that's what I've noticed from talks that I've heard of yours before, and looking at papers as well. It does feel like, part of what you are trying to do is break up preconceptions in all of the various approaches. So there's the the error correction class of folks who are looking at known surface code, color codes, et cetera. Mm-hmm. There's the sort of the experimentalist turned hardware engineers who think they're on the right path to building their transmons or whatever their particular type of qubits, and and then there's the people who are trying to squeeze performance out of the hardware that happens to be available today, and it feels like what you're trying to provoke is all of those individual groups and others. There are clearly others to think about what they may not be considering in their existing approach, sort of challenging the traditional approach, if you will.
Yeah, that's a good way of putting it. I mean, when I have like applicants to the team, and they ask me like how the team functions, and then I'll often say that there's a kind of group style of a type, and even though this may not be verbalized or even not even known to people,
right.
there's some things that are in like just happening in a certain way. And what I often say is that we are like mathematically minded, but still pragmatically oriented. Mm. But another thing I tend to say, and that's not completely untrue, is that I personally like, and that's also a sentiment shared by many people in the team, is that I like to write like first papers on a subject or last papers on a subject. And by that I mean like a first paper is like something crazy,
right.
a wild idea that you throw into the community, and it may start a new field or not do anything at all.
Right.
But it's like a completely fresh like approach to a problem.
Yeah.
And it's going to be like wild or whatever. But at the same time, I also like last papers on the subject. For example, I mean, in the morning we heard a lot about randomized benchmarking, and this is a field where we like try to produce a last paper of a kind where there's like lots of different schemes. I know of over 30 different flavors of randomized benchmarking with different groups, like the Clifford group, the dihedral group, real randomized benchmarking, cycle randomized benchmarking, linear cross-entropy benchmarking. Your head explodes with the different variants. And then it was also not so clear, like in what way the type of data you would expect, namely linear combinations of decaying exponentials, would really come out of the data naturally. And we sat down to formulate like a framework theorem that encapsulated the known schemes of randomized benchmarking and showed in what precise way it's true that if the implementation map is close enough to the anticipated setting, that you really get the anticipated data of exponential decaying functions. And then as a bonus track, we also found an optimal way of getting the classical post-processing together. And why am I saying this? Well, that's not front-page news because it's not something new, but it's still valuable because it kind of formulates a framework. And once the framework is settled, you really know what this kind of machinery is doing, and then you can also progress from there. It was kind of funny because we submitted this to a good journal, and then it was like desk rejected on the first day, saying that we don't publish review articles. We said, no, it's not a review article. It kind of aims at solving the problem. And then, they apologized. Now it's a well-cited article. But it's kind of, the point I'm trying to make is both kinds of work are good work. It's good to be creative and think outside the box. But also to sit down carefully and think an idea until the end.
And tie a bow on it.
Both things are like characteristic for our work.
And what was sort of what's your set of conclusions out of that randomized benchmark? There's limits to how much it can scale. I remember you were saying earlier today that past, I think, 50 qubits or so, there's no real value to the randomized benchmark. Is that? I mean, Joe said something about this in his intro tutorial today. Scaling is an issue. That's right, but there's more pressing questions, like what really the diagnostic information is you can get out of these data, and like what you can infer about the setting you have, like beyond getting like average gate fidelities or something, or whether you can kind of squeeze more detailed diagnostic information out of a randomized scheme. There's a kind of increasing
an increasing understanding of what we can learn about quantum devices meaningfully by suitable randomized measurement schemes that go beyond what the original applications are.
Okay.
I mean, scalability is an issue, but that's not the core issue, I would say. I mean, depending on, I like to say that you can say a lot about little and little about a lot. I mean, depending on what you want, if you think of it like a huge scale system, then randomized benchmarking would not be the right tool. Then you have to think about other methods to kind of certify the function.
Is there any broader relationship between randomized benchmarking and just validation of quantum results? I mean, there's a lot of work going on anticipating, systems that are too large to actually, efficiently simulate. So how do you validate the work that's being done by that system?
Oh, that's a long and winding question. Okay. I mean, you wrote a review article on benchmarking and certification that kind of tries to approach the question. We have a kind of a mind map on the first page that kind of classifies known methods according to the assumptions you're willing to make and the level of detail you want to learn. And many of the known methods can be kind of placed in that two-dimensional diagram. And then what you said, I mean, is a bit fits into the scheme because, I mean, if you have a large-scale system, then you might think about like direct certification schemes.
Right.
And so on. Generally speaking, I mean, in this whole business, there's a couple of like properties you want to see, like desiderata that you want to see fulfilled. And of course, for example, the measurements you want to do or you think you must do should be like experimentally feasible. Then you would want to have a kind of understanding of the sample complexity, like the number of shots. And depending on the experimental platform, this is like super relevant. If you think of like cold atoms, you make an experiment and one click costs like 15 seconds.
Yeah.
You think twice what you do because, I mean, getting good statistics means many runs of the experiment. It takes a lot of time. And also what the community has like painfully learned, I would say, I mean, I have painfully learned it, is that robustness is key. And people speak about SPAM robustness, like state preparation and measurement robustness, in that the preparations are wrong and like everything is a bit wrong. Yeah. But you still want to reliably learn about the property of a quantum system. And that's nice to have, but this is not so easy. And many of these randomized techniques, they are aimed at being like robust in a certain way. And if you can do it, then you should have it. It's not always attainable. I mean, sometimes you have to be a bit more forgiving, but the portfolio is growing of like randomized methods that would also work in a scalable fashion, so that you can assess like the functioning of a big scheme, like of an analog device. And we heard a bit about this morning. Right. And we also have work on that, where the last word hasn't been spoken in the sense that it really depends on what you are willing to invest and what you want at the end of the day. But again, these randomized techniques are basically set up to be specifically robust, which is quite important. Like we have, for example, calibrated, helped the Google team calibrating their Sycamore chip. That was a fun joint venture between our team and the Google team. And there the initial ideas were like super quickly done. We had ideas of super resolution, manifold optimization. We were like super proud of learning the Hamiltonian of that system from data. And then it took us like 2 more years or so to make it properly robust. And once the data came in, the devil was in the detail. And we had to work very hard to overcome certain limitations and make it properly robust. And now we have nicely understood it, and the paper will presumably also come out. We are very happy about this. But robustness is not only key, but it can be pretty nasty and painful. That's the challenge in many cases.
Interesting. And so returning to your talk today, in a way you were I wouldn't say you're closing the books on the sort of potential from NISQ machines and variational approaches to VQE or QAOA or QML, but do you have a sense, are you, I guess, put it simply, are you optimistic or pessimistic for getting sort of valuable functionality out of the type of devices that we can build today? Noisy.
This is an interesting question. I tend to be cautious. I mean, I see my main role as providing tools to fairly assess this. And in the last part of my talk, I have been talking about new work that we did on the impact of non-unital noise on the functioning
Right.
of circuits, with interesting results in the sense that certain non-unital noise gives rise to predictions that seem counterintuitive in a way. And then equipped with those tools, you can see how far you can push things.
Right,
And I was
right.
also talking about error mitigation. I'm not saying error mitigation doesn't work. I mean, I wouldn't say this, but we found certain limitations
Yeah.
concerning their scalability. And these are theorems. I mean, then the assumptions may be wrong or inappropriate, but as they are, they could be wrong, but I doubt that. So one has to work around them somehow.
Yeah.
So my professional job is to provide tools of that type. Now, of course, you can still ask me like, what is your personal viewpoint? I mean,
Yeah.
at the end of the day, does it work or does it not work? I mean, that's maybe surprising to hear, given that I had this like very negative title slide of my talk.
Yeah.
I'm reasonably optimistic. I mean, we know that like we have log depth available, and it's not very. I mean, you don't have very deep circuits. We are
Right.
pretty quickly eaten up by noise.
Yeah.
But log, what does it mean? I mean, it depends on the numbers, like how deep you can really go. And in particular, in the field of quantum simulation, I'm relatively positive that you could do something
Right.
with near-term devices. And I personally like to stay away from hypes.
Yeah.
And if I may say that, to my taste, like the NISQ era was a little bit overhyped
Yeah.
in recent years. People said there's a kind of the wonder weapon. You only have to do variation algorithms, and then you solve like
Right.
the world's big problems and all optimization problems and routing, scheduling,
Yeah.
whatever. And now suddenly people say, oh, you have to become fault tolerant. Before we are like fault tolerant, there's nothing
Right.
you can gain.
Right.
So to my taste, the expectations were too optimistic before.
Yeah.
And they're too pessimistic now.
Right.
And then I say, wait a minute, one must be wrong. And
Yeah.
let's see. So I'm like, I was like, for many years I was comparably pessimistic
Yeah.
compared to many others.
Yeah.
And now I'm comparably
So
optimistic.
you're a
compared to others.
contrarian, is what you're saying, Jens.
Well,
A challenge. You're challenging the status quo.
yeah, I mean, I try to see things in perspective.
Yeah, yeah, yeah. Okay, so last question. You talked about having, either the last paper or the first paper. What are some of the wildest ideas that you're sort of contemplating or working on right now?
Yeah, I'm not.
Without giving anything away, I don't want to steal any of your publication.
Yeah, I mean, I'm for example, I'm pretty. I don't know. I'm not prepared for this question. Like I'm pretty convinced that, for example, like that's an old question, like from the days of my PhD. Like there's a notion of like a resource of entanglement, the so-called distillable entanglement that kind of captures entanglement as a resource. I'm pretty convinced that people tried hard to compute it. It was impossible to do for many people. I'm pretty convinced that like finding out whether a state has a resource character or not, like has distillable entanglement or not, that this is an undecidable problem, a Turing undecidable problem. So people, no wonder people couldn't compute this, because it's kind of basically uncomputable. But maybe more to the point, what I like being an academic, and also what I like to like being an academic outside the quantum industry, although I like to work with the quantum industry, is that you can work on the hip topics of the time. You can work on error mitigation, error correction, fault tolerance, or near-term devices, and all the hot stuff everybody else is working on. But at the same time, you can work on stuff that may not be crazy. It's not really qualifying for your question, but that's really outside the beaten trails. It's like not a hip topic in any way.
Yeah.
For example, we had just 2 weeks ago a paper on a question that I have been fascinated about since many years. It was a core topic of my ERC grant, but not the one I have now, but of the previous one, like from 10 years ago, like how temperature comes about in nature. Yeah, I mean, we know that StatMech talks about maximum entropy ensembles, whereas quantum mechanics talks about pure states that evolve in time. How are these pictures precisely compatible, and can you actually prove under meaningful initial conditions of low entropy, low entanglement, that they would evolve into states that for most times locally look like Gibbs states, that temperature actually emerges as a dynamical feature. And we made really solid progress towards a resolution of that question, which is fun. I love it. And I'm super happy about this. Also because I had this idea a long time ago. And then I gave this to 2 students at a postdoc. And they looked at it and they could make it work in the end after I've tried a lot some time ago. And I'm super happy about this. Also because it's a question that I find important, like how does temperature come about in nature?
Sure.
It's really an interesting question. But it's not a hip question. It's just not the stuff.
It's no quantum gravity.
It's not quantum gravity. It's also not a topic where the big players of the quantum industry are interested in.
Yeah.
But I think it's still an interesting academic question. And in academia, you don't have to decide to do one or the other, but you can, in a way, do both or even get inspired. And actually, we are now working on quantum algorithms based on these ideas.
So very cool.
You can even kind of combine the ways of thinking and be a bit outside the mainstream, which is interesting.
Yeah,
and
I mean that's what I find so exciting about quantum information science, quantum computing, quantum technologies in general, is that there is this very tight sort of interaction between the sort of purely scientific and then the sort of technological development engineering side of things. It may be that this work on temperature, quantum or temperature and quantum systems has some kind of implications for system engineering, right? I mean,
totally. I mean, you started out by asking me you asked me about my personal biography, and maybe I can kind of close the cycle in the sense that this is actually what fascinated me in the first place. That this is a field of research where you can think about basically the foundations of quantum mechanics, the good old questions about what quantum mechanics is about on the one hand, but bring this all the way to technological implications.
Right.
And most of the time you have to decide. You work either on technology and then you are really working on fine-tuned details that are totally remote from the foundations in physics, or you work on the foundations in physics, but then you are up in the sky and you are not connected in any way to technology. But in this field, you can combine the worlds, and that's actually quite exciting.
Yeah, I agree. Well, thank you very much for joining us. This has been terrific.
Thanks.
Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Roney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.